All right. Thank you very much for the invitation. Very happy to be here. Oops, why did my iPad just closed? Yeah. Oops. What's going on? Okay, I need to do something in the settings. Very sorry. It just keeps closing. Yeah, I said never close. Okay. Yeah. Sorry. I hope it will not do it again. So, of course, it's great to celebrate Michel. His work always been an inspiration. So the topic of of my talk maybe is motivated by elliptic algebras, and Michel also worked on elliptic algebras. So I hope it will be of some interest. So yeah, this is based on joint work with Zheng and Nikita Markarian. Oh no, what's going on? It never happened before, sorry. Right, so let me first recall what is Feigin-Odesskii bracket. So this is a Poisson certain Poisson bracket on projective space, which is associated with elliptic curve and a vector bundle on it. So we have elliptic curve C and a stable vector bundle on it. So what we do, yeah, I guess the degree of this stable bundle should be positive. Let's call it N. So the bracket will live on, so this will be Poisson bracket. I will call it P sub C. So it's Poisson bracket on the projective space, which is the projectivization of dual space to the global sections of this bundle, which is, oh no, I'm sorry, I don't know what happened. So this is going to be Pn-1. So the space is, of global sections is n-dimensional, and it's constructed using this realization of this as space of extensions. So we can identify this dual to the global sections as extensions of V by O. And so the construction is as follows. So Poisson bracket you can think of as a skew-symmetric form on each cotangent space. So if you have an extension class, so the cotangent space to this projective space at this extension class, you can identify with orthogonal complement to this line spanned by this class inside the global sections of the space V. So now if you have an extension of V by O, sorry, I need to lower this a little bit. So, and you have two sections here. You need to define a bracket. So you have, sorry, in this orthogonal complement to the extension class, you have two elements, S and T. So you need to define now a number. So what you do is you first take section S, and because it's orthogonal to extension class, it means that you can lift it to a global section of the extension. And now on the other side, you take the other section T, and using the fact that the bundle is simple, the bundle V is simple, you can see that the same condition that T is orthogonal to the extension class implies that you can extend it to a homomorphism from E to V. Okay, and so then what you do is you take So you got this two arrows. So you can take their composition. So you take T twiddle composed with S twiddle. This is again a section of V, and so by Serre duality you can couple it with extension class itself, and you get a number. So this is the definition of the symplectic form of S and T. So it's actually not obvious from the definition that it's not symplectic, skew symmetric. So this not obvious that this is skew symmetric. Yeah, this is unfortunate. But it's actually you can check that it's skew symmetric, and furthermore that it is in fact a Poisson B vector. So this PC, this is a B vector. So it's a global section of lambda squared T on the Poisson space, on the projective space, and so it defines a Poisson structure. So the Schouten bracket with itself is 0, or equivalently the corresponding bracket of two functions is a Lie bracket that satisfies Lie identity. So this fact is actually not obvious at all. The fact that this is integrable, and it can be proven either by direct calculation, which is a bit unpleasant, or it can be deduced from some derived algebraic geometry. So one can consider some derived algebraic stack of complexes on elliptic curve and construct a shifted zero shifted Poisson bracket there, and then deduce from there that this bracket is integrable. Okay, so today I'm going to be interested in the case when this bundle with a stable bundle is just a line bundle. So yeah, so in general, this bracket depends on the curve and on discrete parameters of this bundle, because all bundles are kind of translations of others, so with the same discrete parameters. So there is just two main parameters here, degree and rank, which are known to be relatively prime. And today I'm mostly I'm focusing on the case when rank is 1. So it's just a line bundle. So just consider the case of rank 1. So then we just have line bundle of degree n on elliptic curve, and it gives rise to Poisson bracket on projective space. And so the question I want to study is when two such brackets are compatible. So when they define a Bihamiltonian structure. So let me recall a definition. So if you have two Poisson brackets on the same space are compatible or define a Bihamiltonian structure, if any linear combination, we can just take like any linear combination of this, is again Poisson. So it's again integrable. And this is equivalent to just requiring that in addition to each of them being Poisson bracket, the Schouten bracket between the two bivectors, P1 and P2, is 0. And so the question I want to kind of ask and address today is, so suppose we have two Poisson brackets associated with line bundles on the same projective space, associated with some line bundles and some elliptic curves on the same projective space. So can we decide when they're compatible? And yeah, so a little bit more general, one can consider not just two brackets, but one can consider linear subspaces of Poisson brackets. And so one can ask kind of how large can this bracket, how large can such subspaces containing Feigin-Odesskii brackets can be? Okay, and yeah, I don't know kind of good motivation for this, except that there are interesting. The answer is kind of nice, and hopefully, maybe further work will clarify how maybe there is some kind of reason for this, which can be found in looking at the corresponding elliptic algebras. So that would be, I think, kind of nice direction to extend this. But for now, I'll just tell you the answer. So there is a theorem.
May I use my microphone to ask a question? So you
yes,
do it on the same projective space. So you want to
yeah, I will explain. I will explain exactly how this happens.
Yes. So you have some structure on projective space, like
yes, the structure is normal elliptic curve inside this projective space.
So if you want two, they have two elliptic curves inside one project.
Yeah, exactly. Yeah. So the first basic question is indeed, so you start with two elliptic curves in the same projective space. So they're supposed to be normal. So this means that they have to be degree n plus one, right? And not contained in a hyperplane. So then so each of them, so on each of them you will have a line bundle which is a restriction of O of one. And then then there is an identification of the global sections of one on projective space with global sections of restriction to elliptic curve. And in this way, we see that this projective space of which I was telling here, this projective space, it just gets identified with this very projective space, none other. So right, and so if I have two normal elliptic curves here, I get two Poisson brackets on this projective space, and then I can ask how to ask whether they are compatible just in terms of geometry of this pair of normal elliptic curves. Yeah, Misha, does this answer your question?
Yes, thank you so much. I understood.
Okay, yeah, right. So first, let me give you kind of general construction, which is from our paper with Zheng. So basically, there is a way to construct compatible Poisson brackets when our elliptic curves sit as anti-canonical divisors in some smooth projective surface. So let me tell you this setup. So I will return back to this kind of special case when these are just line bundles, but let me first tell you kind of a general construction. So this is construction of compatible Poisson brackets. So we start with S, which is smooth projective surface. So yeah, we assume that generic anti-canonical divisor is smooth. And suppose we have now a vector bundle on it such that the pair structure sheaf of S and this bundle is an exceptional pair. Okay, so this means that they're both exceptional, and there are no homes from right to left. Right, and in addition, I assume that C1 of V intersect with anti-canonical class is positive, because what I want to do now is I want to restrict this vector bundle to various anti-canonical divisors. And so what will happen in this case is that if I have an anti-canonical divisor, so I can I will have the identification of sections on this V on the surface with its restriction to the global sections of its restriction. And this restriction, by the way, it's going to be a necessarily stable bundle on elliptic curve, and therefore we'll get Poisson bracket on this projectization, which we can now think of as Poisson bracket on projectization of dual to this fixed vector space. So the claim is that in this case, we get actually linear map. We get a linear map kappa from the space of anti-canonical divisors. two bivectors on this projective space. And furthermore, the claim is that the image consists of compatible Poisson brackets. So is a subspace of Poisson brackets. And so the ones which correspond to smooth anti-canonical divisors will be Feigin-Odesskii brackets of compatible Poisson brackets. So, and there is, of course, this would be completely useless unless we can say something about the image being kind of not too small. And for this, we can say something about the kernel. So assume an addition. Okay, so this is the first statement. So there is this linear map and the image is compatible Poisson brackets. And second, so if we assume in addition that this degree of the restriction is bigger than the rank, so assume this, then the kernel of this linear map is entirely contained in the discriminant locus, which is the locus of singular anti-canonical divisors. So this allows to prove that this kernel is not this allows to in various examples to check that this kernel is not big. Okay, so let me give some examples. So let's take S equal P2, just projective plane. So then we have, so to have such an exceptional pair is just equivalent to the fact that this vector bundle sits in the subcategory generated by O of 1 and O of 2. So, and in this case, actually, kappa is going to be automatically injective because everything is GL invariant. And the space of anti-canonical divisors is an irreducible GL3 representation. So, okay, so the simplest is rank 1 case. So if we take V of 1, this is not interesting because we just get all Poisson brackets on P2. Right, so remember the Poisson brackets are going to be on the space of dual space to projectization of dual spaces to sections of V. So sections of O of 1 is just 3-dimensional space. So we just get all Poisson brackets, just all B vectors on P2, right? So there is no condition of integrability, so this is not interesting. But the case of O of 2 is already quite interesting because here we get 10-dimensional family. So the space of anti-canonical divisors on P2 is 10-dimensional. So we have 10-dimensional family subspace, 10-dimensional space of compatible Poisson brackets on P5. And such that the generic one is the Feigin-Odesskii bracket. All right, another example. So we can take S to be a Hirzebruch surface, projectization of O plus O of N over P1. And I think if we take N between 3 and -3, then the space of anti-canonical divisors on S is going to be 9-dimensional. And so we can take line bundles. So we can take here kind of exceptional pair like this. So some line bundle. And in this case, what will happen is that we can get in this case, we get 9-dimensional space of compatible Poisson brackets, which contains any given Feigin-Odesskii bracket associated with line bundle. Poisson bracket on Pn minus 1. Sorry, this is a different n. So n minus 1, which is compatible, which contains any Feigin-Odesskii bracket of type n comma 1. So which means we take line bundle of degree n, and this was actually, this turns out to coincide with construction, which was some kind of ad hoc construction by by Odesskii and Wolf. So these were known to so by the paper of Odesskii and Wolf. Okay, so there is a natural question you can ask. So for which discrete parameters n k there exists at least so there exists a Bihamiltonian structure containing, well, maybe one can ask also even for each elliptic curves, but probably the answer does not depend on elliptic curve. There exists a Bihamiltonian structure containing the corresponding Feigin-Odesskii bracket. Of type nk. So remember, k is rank, n is the degree. So it's enough to consider the case when n is bigger than k, bigger than 0, and n and k are relatively prime. So we know this, of course, in the case when k equals 1. And another case when we know it is when n is bigger than k and n is plus minus 1 modulo k and k is odd. So this is using some using some Delpezza surfaces, but I think this is a kind of nice open problem to find all discrete parameters, given that we know so much about exceptional bundles on Delpezza surfaces. I think this should be it should be possible to understand this completely, but somehow this is not known at present. Okay, so this is maybe a first part of my talk. I can maybe pause a little. So next I'm going to answer so this was construction of compatible brackets. So in the rest of my talk, I will start by assuming that I have two compatible brackets, two compatible Feigin-Odesskii brackets, and I will try to prove that actually in this case there exists some surface from which they come. Okay, are there any questions at this point? All right, so here is theorem number 1. So I'll first consider the case of Poisson brackets on P3. So this means that we're considering line bundles of degree 4 on elliptic curve. So we consider elliptic curves in P3, right? So they are intersections of two quadrics. So yeah, degree 4 elliptic curves in P3. And so for each such elliptic curve, for each degree 4 elliptic curve, we have the corresponding Feigin-Odesskii bracket. And we want to ask when they're compatible. So here is the theorem, which is from our joint paper with Markarian. So for a pair of degree 4 elliptic curves in P3, So P E1 and P2 are compatible. So the corresponding Schouten bracket is 0. If and only if there exists a quadric, surface such that both curves just lie on this surface. So in other words, so each elliptic curve, each degree 4 elliptic curve in P3 defines a pencil of quadrics. So the two curves define compatible Poisson brackets if and only if the corresponding pencils have an empty intersection. There's a common quadric. And we can ask more generally if we have any collection, not necessarily just two, if we have any collection of elliptic curves in P3, when all of them are compatible, so all compatible, this is equivalent to one of two things can happen. Either there exists, so either they all lie on the quadric, such that all EI lie on this quadric, or there is a three-dimensional subspace of quadrics such that each elliptic curve from our family is intersection of two of them. Sorry, is intersection of some, so it corresponds to some two-dimensional subspace in here. So this, so both Q1 and Q2 have to lie in this three-dimensional space. Okay, so let me now explain the proof. So the main part, of course, is one. The second is a consequence of one. So how can we use the fact? So yeah, so direction from right to left. So if we already know that they lie on the quadric, then we can use our previous results. So they of course will be anti-canonical divisors, and from this we can easily derive that they're compatible. So this we already know. So the new part is how starting from assuming that the two brackets are compatible, how do we deduce that they lie on the quadric? So this is based on the following main calculation. So kind of key calculation. Yeah, maybe I should say first that so the first thing we need to know is that so note that this Poisson bracket PE associated with the elliptic curve. So we know that it vanishes, this bivector vanishes on elliptic curve itself. In fact, we know a bit more. So it vanishes on elliptic curve, and so there is this well, because it's three-dimensional space. So if at every point it's either vanishes or bivector can have rank 2. So it actually vanishes on 4 more points, and everywhere else it has rank 2. And what happens is that we have this map from P3 minus elliptic curve to P1, just given by this linear system of quadrics through E. And so there are 4 singular fibers, and the corresponding vertices that will give additional 4 points where it vanishes, and everywhere else it has rank 2. Okay, but anyway, so here is the key calculation. So first, the claim is the following. So we have our elliptic curve in P3, and we take some point in it. So then we can, and suppose we have some other, so we have our bracket PE, and suppose we have another bracket P. some other Poisson bracket, some other, in fact, just B vector, some B vector on P3. And suppose we know that the Schouten bracket of Feigin-Odesskii bracket PE and this other B vector is 0 at the point P. Then it implies that B vector P at point P is, well, it's always, of course, decomposable because just in three-dimensional space, but the claim is that one of the vectors is going to lie in the tangent space to the elliptic curve E. Right, so this B vector, of course, is always decomposable, so you can write it as product of wedge product of two vectors. But the claim is that if this Schouten bracket is 0, one of these vectors can be chosen to be in the tangent space to E. Yeah, and the second part that we need is that if we consider the canonical distribution associated with the Poisson bracket, so if we consider image, all right, so we take some point not on the elliptic curve, but let's take this point away from elliptic curve, and also not on one of the not a vertex of one of the singular quadrics. So then there is a unique quadric which contains this point and contains E. And the claim is that the corresponding two-dimensional space, this tangent space to this quadric, sorry, not at P, at X. So this is exactly the canonical distribution associated with the Poisson bracket. This is the image of the cotangent space to P3 to tangent space to P3 at this point. Okay, so using this, we can give the proof of the theorem. So very easily, so suppose we have two elliptic curves and the corresponding Poisson brackets are compatible. So then we take, so yeah, we can assume that E1 is not equal to E2. So, right, so then we take a generic point of E1. And so then we apply this first key calculation. So by 1, we get that the tangent space to the first elliptic curve is contained in the image of PE2 at this point. Yeah, which is sits inside tangent space to P3 at this point. But on the other hand, by 2, we know that this image is exactly the tangent space to the quadric passing through E2 and this point E, and this point P. So this means that if I consider this projection from P3 to P1 given by the quadrics through elliptic curve E2, so and I consider now E1 sitting inside P3 and compose with this map, then we see that this composed map everywhere has 0 derivative. Because what we just observed, this quadric, this is a fiber of the map from P3 to P1, and we see the tangent space to E1 sits inside tangent space to this quadric. So this means that this map is constant. This map from E1 to P1 is constant. And this means that E1 sits inside its fiber, which is one of the quadrics. Okay, so let's see. Right, so maybe I can explain a little bit this first key calculation. So how do we prove this? So this is actually based on the following general fact. So how do we calculate the Schouten bracket at the point P inside E? Yeah, we just need this. So this is based on the fact that we can, so PE at this point is 0. So, but we can also consider further information about. So we can actually consider linearization of this. So also can be computed of this Poisson bracket. So basically, right. So basically, when we write this PE as I don't know, in some basis. So here we know that the kind of values are going to be 0, but here there will be some linear functions in these coordinates, and this can be determined because they actually come from the structure of the Lie algebra. So the Poisson bracket, when Poisson bracket vanishes at some point, the cotangent space to this point, so we get Lie algebra structure on the cotangent space to this point, which is just given. So if we think of this cotangent space as maximal ideal modulo maximal square, it's just induced by the bracket of functions. So the point is that the fact that it vanishes means that the bracket of maximal ideal with maximal ideal lies in the maximal ideal, and therefore we have a well-defined bracket on M mod M square. So this actually can be very nicely identified. And this is a general calculation. So in terms of extensions, so this is not only for P3, but in general. So so we can calculate. So so we have the corresponding extension. So there is some bundle here, going to some line bundle here, going to O. So this is our, this is, in this case, this is degree 4 line bundle. But the point is that the cotangent space to the projective, yeah, this is also true if this is a degree n bundle. So the cotangent space is going to be identified with H naught of L. Well, actually, with it sits inside. It's a hyperplane in H naught of L, which is orthogonal to the class of extension. And so there is natural algebra associated with this extension. Namely, you just take all global endomorphisms of this bundle and mod out by identity. And so in general, this maps. So this so there is a natural map from here to H naught of EL, which actually lends in this orthogonal to the extension class. And the map is simply, if you have this endomorphism A of V, you send it to A and you post-compose it with P and pre-compose it with I. And this will be an element in H naught of L. And so the claim is that this gives a Lie isomorphism. This for any extension, this induces an isomorphism of this end V mod identity with kernel of the Poisson of the map given by Poisson B vector from cotangent space to tangent space. And there is always a Lie algebra structure. This is compatible with Lie algebra structures. Now, in the case when you take extension corresponding, so extensions corresponding to points of elliptic curve, so they are of the form so the bundle in the middle is going to be O of P plus L of minus P. And here it's very easy to calculate endomorphism algebra. So there will be an algebra with n minus one dimensional algebra. So there will be an abelian subalgebra and one more element. So this is abelian subalgebra, and bracket of y with each xi is just xi. And so using this information, so we can calculate the linearization of Poisson bracket. And so this then can be used to calculate the Schouten bracket and gives us key calculation which used to prove the theorem. All right, so let me now explain the general case when it's not necessarily P3. So now assume we have, so now consider high dimensional case. So consider normal elliptic curves in Pn. Where n is bigger than 4. So actually, the case in some ways similar, but there are some differences. So the main point here is that we again want to consider certain surfaces. Now the surface. So suppose we have such normal elliptic curve inside Pn. So first of all, there is a natural three-dimensional subvariety containing it, namely secant variety. So we can consider all secants of E, right? So we have our elliptic curve. So we take pair of points and we consider lines, and then we take unions of all lines, and this will be three-dimensional guy. So this has natural map to peak 2 of E. Well, it's a rational map, so if we throw away E, it becomes regular, right? So you can just, so if you have a line with, which is determined by points x, y on elliptic curve, right? So you send it, you send any point on this line to x plus y, to O of x plus y, which is a degree 2 line bundle on E. And so we can fix some line bundle here, and then we can consider the preimage, and this will be a surface containing E. So we have this family, so we get this family of surfaces. So for each curve, we have this one-dimensional family of surfaces, which is parameterized by L in peak 2. So this is an analog of this pencil of quadrics. So in the case of P3, we had this family of surfaces, namely quadrics, which was parameterized by P1. So what's different in the case n at least 4 is we again have a one-dimensional family of surfaces, but it's not parameterized by P1. It's now parameterized by elliptic curve itself. And now the theorem is kind of has the same flavor as before. So suppose we have a pair of elliptic curves, of normal elliptic curves in Pn of degree n plus 1. So then the claim is that the corresponding Feigin-Odesskii brackets yes, so they are compatible if and only if, yeah, maybe I'll if and only if one of two things happen. So either there exists either the corresponding kind of one-dimensional families have one element in common. So by the way, this SLs, these are ruled surfaces. So they're what's called rational normal scrolls. And one can even determine their types. So I will just call them, this will be family of scrolls. And so either there exists a scroll, a rational normal scroll, which contains both curves, or n equals 5, so this is P5, and there exists a Veronese surface. So there's embedding of P2 into P5 such that both elliptic curves sit here. So this second example, this precisely corresponds to this family of Poisson brackets I described in the beginning, associated with anti-canonical divisors in P2 when we take a line bundle of 2 and restrict it to all of them, to cubics in P2, and this precisely gives you this compatible Poisson brackets on P5. Right, and there is a similar statement. So similar statement when there is more than 2. So I'll just omit it. So here the proof uses some additional ingredients. So the main additional ingredient is we need to know that for elliptic curve, for normal elliptic curve in Pn, where n is at least 4, so when does the Poisson bracket has rank equal to 2? So suppose we take some point not on elliptic curve. Well, clearly, if point is on elliptic curve, the rank will be 2. So the claim is that rank is at most 2 at this point, if and only if this point of projective space lies on the second variety of E. And right, and so furthermore, yeah, so furthermore, so the same statement as before we had for quadrics. So so when rank is equal to 2, right? So maybe I should actually state equals to 2 here. So it cannot drop so outside of elliptic curve in this case. So in fact, the corresponding two-dimensional subspace, if I take image of P going from cotangent space to tangent space, this is exactly the tangent space to the corresponding surface SL, which passes through this point in the second variety. So in the case of P3, this was tangent space to the quadric. Okay, so now this is almost correct, except that there is one exception. So this is almost true. So if this is true, if n is not equal to 5, so it's either this or there is a special case when n equals to 5 and the curve sits in the Veronese of P2. Sorry, not the curve. The curve sits in the Veronese and the pole. Yeah. Okay, so I think I used up my time. So maybe I'll just say at the end, one corollary from this theorem. Okay, I will not write this, just say it in words. So in the case when this is even dimensional projective space, P, like P4, P6, and so on, one can prove that in fact this spaces obtained from this anti-canonical divisors in fixed scroll, they are in fact all maximal subspaces of compatible Poisson brackets containing some Feigin-Odesskii bracket. So for example, if you take Feigin-Odesskii bracket on some P of even dimensional projective space, the maximal dimension of subspace of Poisson brackets containing it is at most 9 if this is not P5. Oh, sorry, well, yeah, it is at most 9. Sorry, stop. Yeah, so P5 is odd dimensional, right? So it's at most 9 dimensional, and it appears from elliptic curves contained in some scroll. So this follows from our theorem together with the fact that on even dimensional projective space, all Poisson brackets in a neighborhood of one Feigin-Odesskii brackets are also Feigin-Odesskii brackets. This is a result of a work of Pim and Schedler, which uses a very nice property of Feigin-Odesskii brackets on the even dimensional spaces, that they are actually what's called holonomic Poisson varieties. But yeah, but that's probably enough. Okay, so I'm